Hi, everyone. I'm delighted to be here today to present our research titled FAMOS, Robust Privacy Preserving Authentication on Payment Apps via Federated Multi-Modal Contrastive Learning. My name is Yifeng Cai, and I have the privilege of working on this project with my colleagues. This paper represents our efforts to address a burgeoning issue in the real world, the security authentication service in the payment apps. So, as of 2024, one of the modern payment app in China, Alipay, like my t-shirt, yeah, here, has more than 300 million daily active users and more than $20 million in the daily payment. So all the payments need to be carefully protected. However, the traditional authentication methods such as passwords or biometrics are vulnerable once the device is compromised. For example, the online attacker may already obtain the user's password in a data breach, and children may already know their parents' passwords or already save their Face ID or Touch ID in their parents' mobile device. Then they can make purchases or reward online celebrity in TikTok, maybe without their parents' permission. Therefore, the payment apps need to discover a more reliable authentication service. The Authentication and KDAuth emerged as the total solution for transparent and user-friendly authentication service. They utilize the built-in sensors to capture distinctive user behavior patterns in an imperceptible manner. Thus, they can prevent unauthorized payment and do not harm user experience. However, they face two key limitations in deployment to the payment apps. The first limitation is they didn't consider the negative influence of background activities on sensor readings in real-world scenario. They all assume that users should keep stationary and take similar actions when using the mobile apps. However, users are not always stationary, right? For example, as shown in the figure, users may use their phones under different background activities like walking or lying on the bed. These background activities introduce noises to the sensor readings, making it difficult to observe the subtle user-specific patterns. Specifically, the sensors are showing different stability under different background activities. For example, in the right figure, the accelerometer can capture more user-related activities when the user is lying compared to the user is walking. Conversely, for walking, the touchscreen sensor can better capture the user-related activities when previous methods directly utilize several sensors to authenticate users. The noises will significantly downgrade the accuracy. And the second limitation is that the violation of user privacy in the sensor data. Their training strategy requires one user's data as positive sample and other user data as negative sample. But collecting and sharing such data is naturally against regulation, for example, the GDPR in EU and the PIPL in China. So we have two key insights to tackle this challenge. The first is fusing multimodal sensor data. We can effectively eliminate the background activities. We can see in the figure when we utilize several sensors to authenticate users, we can fuse them to obtain a high-quality feature. We can arrange a high weight to the stable sensor feature and give a lower weight to the noisy sensor feature. This strategy can effectively mitigate the influence of noises and maximize the contribution of the stable sensor. And second is clustering one user's data representation by the action categories. Then we can achieve the user authentication without training data from other users. Because previous approaches, like in the left figure, converge to the suboptimal in the practice, since different actions and their different background activities of the same user could be quite different. In addition, their naive strategy need other users' data as negative sample. Therefore, in our insight, we cluster the representation vector of the same action close to each other and push other actions far away. This design also makes it unnecessary for us to rely on the other users' data as a negative sample. So in our design, we want to achieve 3 goals. The first one is robustness. The FAMOS should be robust to noises introduced by the background activities. So we fuse the multi-modal sensors to extract more information and mitigate the side effects of the noises. And the second goal is lightweight, because FAMOS should be deployable within the user smartphones. So we design a residual DNA model architecture to achieve good performance while minimizing the model size. The third is privacy preserving. FAMOS should prioritize user privacy, minimizing the risk of data leakage. Therefore, we leverage the federated learning paradigm, which ensures the privacy-preserving training while ensuring the accuracy. So our training phase is shown in the figure, and first is the sensor fusion module. The goal of this module is to fuse the readings from different sensors. After using a specific encoders to extract the features, the module 1 utilized the attention mechanism to dynamically assign the importance weight to different sensors and generate the fuse features. This can enable us to automatically select stable sensor readings and different background activities. And the second is constructive learning module. This module is to cluster the representations of the same action while pushing those from different actions far away. The FAMOS can categorize the representations into several compact clusters based on different actions. As shown in the right figure, the P1 and P2 represent 2 positive actions, and N1 and N2 represent 2 negative actions. And this module minimizes the representation distance from the same action and maximizes the distance from different action. So after training, the user's data sample are distributed to corresponding cluster based on the action representation, while the data sample from other users are excluded by all clusters due to the features dissimilarity. And last is the federated learning aggregation module. This module aims to aggregate the general knowledge from the user-side model while leaving the user-specific knowledge on the device. This module takes the locally trained user model as input and output and aggregating module. The aggregating module is sent back after the aggregation. And after all the training phase, the FAMOS can use the trained model to authenticate users on the devices. So in the evaluation part, we want to answer the 5 research questions. First is how is FAMOS performance compared to the existing solutions? And second is how well can FAMOS mitigate background noises effectively? And third is can construct learning cluster actions from different users. And the fourth is can federated learning improve the performance and facilitate the training process. And last is how is the on-device performance of the FAMOS. So our protocol, including the data sets, we collect 2 different data sets. One is the real-world data set. We collected 70 real-world Alipay users to play as 20 victims and 50 attackers. And the in-lab data set is for the further analysis. We hired 24 volunteers in AND group to play as 4 victims and 20 attackers. The data is including the touchscreen sensor and 3 MU sensor. And we use 4 different devices to evaluate the on-device performance. The baselines we choose is the Authentication and KDOS and metrics, including FAR, FR, ER, TPR, FL score, and AUC, and so on. So the first is the overall effectiveness. You can see in the figure, we can achieve 4.4 times lower in FAR and 5.5 times lower in FAR. And in the AUC, we can achieve the 27.7% higher And in F1 score, we can achieve 42.2% higher compared to the baselines. And second is to how FAMOS mitigating the background activities. First, we investigate the improvement on accuracy by sensor fusion. We can see that we can get up to 31.9% improvement by this sensor fusion compared to using a single sensor to authenticate users. And second, we investigate the effectiveness of attention. We can see that different sensors have different stability and their different background activities. And using our attention mechanism, we can give a suitable attention weight to different sensors and their different background activities. And in the RQ3, we can see that compared to the average distance of fused features, our representation by the constructive learning can obtain 1.4 times increasement in the difference between sample. And the four is effective of federated learning. We can see that without federated learning, the FAMOS local will have a 15% lower than the FAMOS. And the last one is the on-device performance. We can observe that FAMOS run with relatively low overhead on devices, which means FAMOS can provide robust authentication services without disturbing users' daily usage in payment apps. So in conclusion, we first identify two practical limitations: the influence of background noises and privacy violations that impede the deployment of SOTA user authentication solutions to real-world applications. Second, we propose a novel authentication framework, FAMOS, based on federated multimodal constructive learning. FAMOS can robustly authenticate users and their noisy background activities without compromising user privacy. And the third is we comprehensively evaluate FAMOS using real-world datasets and devices. Experimental results demonstrate the robustness and efficiency of FAMOS in the real-world scenario. Thank you.